Hello everyone, my name is James Yoon, and for this final project, I'd like to discuss how brain-computer interfaces, or BCIs, are being used to restore communication for people who can no longer speak. By the end of the presentation, you'll be able to explain how neural activity related to speech can be decoded into words, and you'll be able to analyze recent clinical applications of BCI for communication, along with their current limitations. I'll keep the focus on the mechanisms that are easy to visualize and on concrete patient results. As we discussed in class, speech production depends on a network that includes Broca's area for planning and the primary motor cortex for controlling the articulatory muscles. Damage to these regions or to the corticobulbar pathways disrupts the neural commands needed for speech, leading to conditions such as anarthria, the loss of speech, despite intact language comprehension. BCIs target intact planning signals in these cortical areas, bypassing damaged pathways to restore communication. A speech BCI follows a sequence that mirrors the pipeline you see on the slide. First, the system records neural activity, for example, with electrocorticography on the cortical surface or with scalp EEG. And secondly, the signals are pre-processed to remove noise and to segment the stream around the attempted speech event. And third, a decoder maps patterns of activity onto linguistic units. Modern decoders are data-driven and use machine learning to learn these mappings from many training trials. And finally, the output appears as on-screen text or as a synthetic voice, and the user receives immediate feedback, which supports learning and improves accuracy over time. In a landmark study at UCSF, Moses and colleagues implanted a high-density electrocorticography array over the speech sensory motor cortex of a participant with anarthria following a brainstem stroke. The participant attempted to speak while the system recorded broadband cortical activity. The pipeline you see illustrates the steps: neural signal processing, detection of speech events, classification into word probabilities, and sentence assembly aided by a language model. The participant produced sentences in real time at an average speed of about 15 words per minute with approximately 74% accuracy. This was the first demonstration of restoring free, continuous speech to a person who could not vocalize at all using direct cortical decoding. A different strategy came from Willett and colleagues at Stanford. Instead of decoding attempted speech, the system decoded imagined handwriting. When the participant imagined writing letters, distinct neural trajectories were recorded and fed to a recurrent neural network, which output letters that a language model assembled into text. This approach achieved around 90 characters per minute with over 94% accuracy. In practical terms, 90 characters per minute corresponds to roughly 15 to 18 words per minute, depending on spacing. So the key insight is that handwriting representations in motor cortex are separable and therefore highly decodable, which opens another path to rapid BCI communication. Here is the side-by-side comparison of the both experiments. Both systems are invasive in their current clinical form. Moses used electrocorticography on the cortical surface, Willett used intercortical arrays, and these choices yield high-quantity signals, yet they require surgery and long-term device management. Now, to the limitations listed below the table, surgical implantation carries medical risk. Users typically require extended training, and the decoder often needs a recalibration process across days as signal properties drift. Brain data raise privacy and consent questions since neural patterns can, in principle, reveal sensitive information. And finally, model reliability matters. Performance can vary with fatigue, medication, or attention, so robust error handling and user control are essential. Stepping back, the key message is that BCIs are not only about transmitting text, they're about restoring a person's ability to participate in conversation. The communication rates you saw are still far below natural spoken language, which averages well over 100 words per minute. Yet, for someone who has no usable voice, even 15 words per minute can change daily life. Looking ahead, improvements in signal stability, adaptive decoders, and less invasive recording may bring higher speeds and greater reliability. I've included two peer-reviewed sources that anchor the results discussed today, Moses et al. 2021 in the New England Journal of Medicine, and Willett et al. 2021 in Nature. Thank you guys for watching.